Section 1.5 is continuity. So whether or not a function is continuous. And this is a key concept in calculus, probably a very natural step from the limit into the idea of a function being continuous. So the definition of a function f being continuous at a point A, in other words, a number A, is the following. If the limit as x approaches a of f of x is equal to f of a, then the function is said to be continuous. So this is really why polynomials and rational functions are easy to evaluate their limits inside of their domains, right? Because it turns out that polynomials and rational functions are continuous on their domains. So we're going to see that as a theorem in this section before it's all through. So a theoretical thing to note about this definition is the following. In order for a function to be continuous, there are really three things that have to be true or have to happen. First, the limit as x approaches a of f of x has to exist. There has to be some real number that comes out of this limit. Secondly, the function has to be defined at a. F of a has to have a value as well. Remember, a is any real number that we might be considering in the domain of f. And then lastly, not only do each of these two things have to exist, but they have to be equal to each other. So if any of those three conditions fails, there's no limit, or the function's not defined at a, or those two things aren't equal. If they both exist, then the function fails to be continuous at that value a. Okay, so those are the three ways a function might be discontinuous. So let's have a look at an actual example, or a few examples dealing with discontinuity versus continuity. So the example asks us to identify where each of the given functions is discontinuous and state which condition is not satisfied for each discontinuity. Okay, so we're going to spot where the function is not continuous, and we're going to say why, what failed in that situation. So let's see, our first function here in part A, this f of x is a piecewise function. It's given as a rational function, 1 over x plus 2, for x values that are not equal to -2. So this function somewhat wisely or astutely has thrown out the value of -2 from this rational function, which is where that rational function would be undefined anyway. And the function instead says if you give this function the value -2, it gives back the return value of 1. So it's kind of patched up the problem at x equals -2 of this rational function. Now let's see whether or not this function is continuous there. So, we're curious. -2 is obviously the problem, okay? F of -2 is just 1, right? So if we plug in -2 to this, like I said earlier, note this, f of -2 is equal to 1. So that's one thing that's easily seen. So that's not a failure point, right? The function's defined at -2, its value is 1. Okay, so it's well defined when we evaluate the function at the point. The next thing we need to check then is what is the limit as x approaches 2 of f of x? Well, we're not sure about a two-sided limit. We might check a not a two-sided limit. If we check this function, we've done plenty of examples like this, what we'll realize is that the limit as x approaches -2 of f of x just simply doesn't exist, right? Remember, even, so what I might point out is this. On our way to finding that limit, we would probably, go back to some techniques of section 1.3. We'd approach from the left of -2. So these are things like -3, -2.1, -2.001, numbers to the left of -2 of 1 over x plus 2. And what we'd realize is something like -2.1 plus 2 is -0.1. That's a negative number, and it's getting larger and larger as we get closer to 2 on the left side. So we're approaching negative infinity. And I'll let you work that out either with a table or some other means of reasoning. Similarly, remember that this is the same as does not exist, right? This just, in the sense that this function diverges at the point x equals -2, right? It doesn't have a limit there. Negative infinity, infinity only describe the way in which a function diverges. It doesn't mean that there actually is a limit there. It's just telling you how the limit doesn't exist. And in this case, we'd find that as we approach -2 from the right, these are -1.9, -1.99, then we get positive infinity. So even if negative infinity and positive infinity were, valid, information for the limit to exist, they still don't match, right? They're not equal to each other. And so the two-sided or the one-sided limits, the two one-sided limits are not equal to each other. So the two-sided limit does not exist. Remember, that's a condition for a two-sided limit to exist, is that both the one-sided limits exist and are equal to each other. In this case, as soon as we saw this first infinity, negative infinity show up, we're done. This function does not have a limit there. It diverges at the point x equals -2. So this function fails to be continuous simply because the limit as x approaches -2 does not exist. Now, all of this was just review of how to do things from section 1.3. So if that was a little bit confusing, maybe you go back and have a look at those problems again, and possibly even the video or the book examples. Okay, moving on to our second example, part B here, we're given a function g of x. And g of x is equal to x squared minus 2x minus 3 divided by x minus 3. This is a polynomial, a quadratic specifically, over another polynomial. That's a linear function in the bottom. Be more explicit about it. And so this makes it a rational function, right? We have a polynomial divided by a polynomial, so we're dealing with a rational function. Now, there's something a little suspicious about this rational function. Perhaps I can factor this quadratic polynomial. And it turns out I can. And it's worthwhile to do so because it'll make evaluating our limits and even our function values perhaps a little bit easier to deal with. So when I do that, I get the following. I can factor x squared minus 2x minus 3. Remember that possible factors are plus or minus 3 and plus or minus 1. But anyway, however you go about factoring, you should arrive at x minus 3 times x plus 1 is the factorization of that quadratic. We're dividing that numerator by x minus 3, and it turns out we have a common factor of x minus 3 in the numerator and denominator. So we can cancel that factor, and we end up with just an x plus 1 as our result. But remember when we do this, that our original function, even though it's equal to this function, we still maintain our original function's domain. Sure, we canceled x minus 3 out, but it still remains for us to preclude the value 3 being plugged into this rational function or this function g at all. So we cannot allow 3 to be in the domain. So g of x is equal to x plus 1 for all values except for x equal to 3. So we can't allow x equal to x to be 3. And in this situation, especially when we look here, we see that g of 3 is not defined. And that automatically tells us that we're going to be discontinuous at such a point, right? G of 3 is not defined. So whenever a is 3, our function's not defined, right? So this fails because the function's not defined at x equals 3. So g is discontinuous at x equals 3. All right, no other values are affected, right? We don't have to throw any other values out of the domain. If we check the limits of this function for any other x values that aren't 3, we'd see that the limit of g of x as x approaches that number is equal to g of that number, right? And then lastly is this function h of x. It's also a piecewise defined function, much like the first one given to us. And this looks like a repeat of g's information, right? It's the function g. And then it's defined for all x values except for x equals 3. And then what h does is it fixes the fact that g wasn't defined at x equals 3 by saying, well, let's just make that value 1. So if I plug a 3 into this function h of x, it's just going to say, okay, x is 3, so my return value is 1. I'll return a 1. Now, any other values you plug in, you run through this formula up here, anything that's not 3. Okay, so it turns out h is discontinuous at x equals 3. And of course, these are the suspicious places to look, where the function changes behavior or anywhere you might throw out values from the domain of a function. That's where you want to consider failures in continuity for functions, or anytime you might suspect a vertical asymptote in any kind of function. So it turns out it is discontinuous at x equals 3, but let's see why. We take the limit as x approaches 3 of this function, that's this expression right here, it turns out it's equal to 4. Remember that, and there's some information going on here, remember above we factored this function and then canceled x minus 3 to get that this expression here is actually equal to this x plus 1 function once it's simplified, only it's not defined at 3. So taking the limit as x goes to 3 of h of x here tells us to use this expression, right, from this line up here. Those are all the values around 3 but not equal to 3. Okay, and when we do that, remember we can cancel this down to x plus 1. And now this is a polynomial, so we can just use our plug-in rule or substitution rule. So this is x plus 1, so it becomes 3 plus 1, and our limit as x approaches 3 is 4. Okay, so it turns out the limit of h of x exists as x approaches 3. And the last thing to check is this, that limit is 4 as we have highlighted down below, but if we look at h of 3, then we realize that h of 3 is actually 1, right? We've already seen that whenever x is 3, h gives us the return value of 1. 1 and 4 are not equal, right? So this fails that final check of discontinuity. Though the limit exists and is equal to a real number, in other words, and the function's defined and that it's equal to a real number at that point, these two values aren't equal to each other, so the function's discontinuous. So those are the three examples of 3 different ways a function can fail to be discontinuous. Now, the bottom tells us to name the types of discontinuities observed in the above examples. So each one of these discontinuities is of a certain type, and we should be somewhat familiar with these. So if we go back through, let's go back up to the top, and we'll look at each one of them. So this was the situation where the limit does not exist, right, for some function f of x. If that's a rational function, the limit doesn't exist, then what we have is this is an infinite discontinuity. And remember, that can also be seen by these limits right here, right? If the limit of a function at a point is infinity or negative infinity, then that's going to end up being an infinite discontinuity. So that's the way to know that. In other words, there's a vertical asymptote in the function, and that's where the problem is. Infinite discontinuity is this type right here. I'll spell the whole thing out once. Discontinuity. Okay, so those are clear on the graph because they have vertical asymptotes and they shoot up along those vertical asymptotes. Now part B. Remember, B failed because g of 3 was not defined. So, in other words, all around this function, all around the value 3 actually, the function has no problem. X plus 1 is well defined for all values around 3. Remember, our function has to exclude 3 because of its original definition. So x plus 1 is just not defined at 3. So really, we've plucked the point 3 out of the line x plus 1. We've removed the value at x equals 3 from the line y equals x plus 1. This is called a removable discontinuity. So it'll just look like a line with a little hole in it, a little open circle. Removable discontinuity. Oh, this is terrible spelling in the first one, I just realized. Continuity. Just a whole block there. Removable discontinuity. So this one, we punched out a hole in the line at x equals 3. And the last one is what now? So the limit of this one existed, and the function was defined there. However, they didn't equal each other. So this one is a jump discontinuity. jump discontinuity. So in other words, rather than the function being equal to 4, right? This function, as x approaches 3, the curve, the y values approach 4, but for whatever reason, the function's defined as h of 3 equals 1. Well, 1 doesn't match up with the values that the function's approaching, so the function essentially jumps from where it's approaching 4, it jumps down to 1 instead of going to 4. We could make this function continuous simply by going right here and saying, okay, let's change that 1 to a 4, and that way it'll match this number, so these two things would match up, and then the function would be continuous. So that fixes that jump discontinuity. So that is those are the 3 discontinuities that we'll see. It's nice to know which one's which, because then you can identify graphs of functions from their well, you can identify a function from its graph and be able to pick it from a list and know which one's which. Classifications of discontinuities. Okay, so the idea of being continuous from the right or continuous from the left at a number A, so just like having a two-sided limit within one-sided limits that are connected to it, we can be continuous, we can be left-hand or right-hand continuous, or one-sided continuous at a number. So these definitions are given as this, right? So we kind of touched on that on the previous page's first example, where we looked at approaching, I think it was -2 from the left or from the right, to see whether or not we are left or right continuous, or to see even if the limit existed at all. But here, let's go a little bit further into this. So we're going to introduce a new function. You've probably never seen this function before. It's an interesting function. It's the greatest integer function of x, is what it's called, or the floor function sometimes. It's written as with these sort of half brackets with the legs on the bottom. It's defined as the largest integer that is less than or equal to x. Okay, so it's the largest integer that's less than or equal to x. So this is an interesting function. If we remember, integers are whole numbers, positive or negative. Okay, if we give this function an integer, 1, what this thing is doing is it says, what is the greatest integer that is less than or equal to 1? Well, 1 is less than or equal to 1, and that's the greatest integer that is so. So the output's 1. Now, more interestingly, if we give it 2.5, what is the greatest integer that's less than or equal to 2.5? Well, you can count up 0, 1, 2. 3 is too large. It's not less than or equal to 2.5. So 2 is the greatest integer that's less than or equal to 2.5. Remember that pi is approximately 3.1415, so on, right? So the greatest integer that's less than or equal to pi is 3. And so the output is always a whole number. So the graph of this function, interestingly, looks like the following. From 0 to 1, all the values, all my x values along this interval here are things like 1/2, 3/4, 1/9, 9/10. All the numbers that are less than 1 but greater than 0 fit along this interval. And the output, notice, of the function is 0. It's a flat line. And all the y values along this interval are 0. So if I said, what's the greatest integer function of 1/2, it would be 0. And that's what the graph is telling me here. And it's that way all the way until we get to 1. And then it jumps, because the greatest integer that's less than or equal to 1 is 1. And here it is on the y value here. And then we switch to these values. So then numbers like 1.5, 1.75, 1.8, I don't know, 1.33 repeating, right? Those are all numbers that have an output of 1. So, and the function continues to jump every time we get to a new integer. Once we get to 2, 2 is now the greatest integer, or the greatest integer that's less than or equal to 2, and so on and so forth. So what they're going to ask us is to evaluate some limits here of this greatest integer function. It looks like we're going to focus on the x value 3, but we could focus on any given integer that we like if we wanted to really assess this thing. So in our case, we want to determine whether or not this greatest integer function is continuous at 3. Okay, so we're really specifically looking at the x value of 3. So we need to approach it from the right to see if it's, from the left to see if it's left continuous. We need to approach it from the right to see if it's right continuous. And if it's left and right continuous, well, then it's probably continuous overall, but we'll see that later on, right? So let's have a look here. Well, let's think about the first one. The limit as x approaches 3 from the left of the greatest integer function of x is 2. Does that make sense? We're approaching 3 from the left. So here we are. We're moving towards the x value of 3 along this interval, right? That's what this little arrow here is telling me. I'm moving along the x-axis down here. But these are values like 2.5, 2.7, 2.9, right? So the greatest integer that's less than or equal to 2.7, 2.9, all those numbers is a 2. And we don't quite allow a 3 to be plugged in here because we're taking the limit as x approaches 3 from the left. So we just end up only ever getting a 2 out for anything on this side. So it looks like the limit, or turns out that the limit as x approaches 3 from the left of the greatest integer function of x is 2. So hopefully we've convinced ourselves of that. All right, now let's see. The limit as x approaches 3 from the right of the greatest integer function turns out to be a little different, right? So here we are at x equals 3. We're going to approach with x values on the right-hand side. This is 3.1, 3.01, things like that. The output of that function, you can just simply see it in the graph, but if we think about it, what's the greatest integer that's less than or equal to 3.1? Well, that's 3, right? There's no integer greater than 3 that's less than or equal to 3.1. So there it is. So we get 3 out here. And so that tells us our limit in this case. We can see it. We're approaching 3 from the right as we move towards 3 from the right on this x-axis. So our limit in that situation is 3. So from the right, it's 3. From the left, it's 2. And something will tell us that, well, it's probably pretty easy to know that this function actually doesn't have a limit as x approaches 3. Right? Because the left-hand limit and the right-hand limit aren't equal. Though it has left-hand limits and right-hand limits, they exist, they're not equal. So the limit of the function as x approaches 3 does not exist. Okay? So this limit doesn't exist, right? So that we know that there's going to be a discontinuity of this function, right? So we know that at x equals 3, the greatest integer function is discontinuous. We knew that anyway, because when we looked at 3 here, on either side of it, as we approach 3, we jump, right? We're moving along here, then all of a sudden we jump up to this level. So there is a jump discontinuity that happens. All right, so was the function left continuous or right continuous anywhere? Well, what we need to evaluate now is what is f of 3? That's sort of the last thing on this list that we need to check is what is f of 3, right? That's what we want to ask ourselves. Because if f of 3 is equal to either of these limits here, this one and or this one, well, then we know that the function is left or right continuous based on that. Well, the greatest integer function of 3, the integer that's the greatest integer that's less than or equal to 3 is 3, right? Does that match either of our two limits? It matches our right-hand limit. So it turns out that this function is right continuous, as we've listed right here. So that's how we conclude that. If we look in the picture, the way we see that is it's right continuous because remember open dots versus closed dots in graphs. So if you happen to be able to graph this nicely, and once you've graphed it once or twice, you should really have the hang of it. You realize that these are all y values of 3 moving along this interval, and the function value itself here at x equals 3 is 3, as opposed to the left-hand side, which all these values, y values, are approaching 2 as we approach 3. However, the function's not defined as 2 there, it's defined as 3 there. So that's why we see it. These approach an open dot, so it's not left continuous. These approach a closed dot, so it's right continuous. Now you won't always have to graph to do that. You'll have to do this analytically by matching function value with left and right hand limits. But if you do have a graph, that's a nice way to see what's going on. It's a nice way to learn left and right continuity. So being continuous on an interval. So far, we've only talked about whether or not a function is continuous at a given point. So a function f is said to be continuous on an interval if it is continuous at every number in the interval. So if we can show somehow that a function is continuous at every a in some given interval, then we'll know that the function's continuous on that interval. Okay, so notice that in interval, we might have a left endpoint and a right endpoint. So f can only be one-sided continuous at either endpoint of an interval. So we'll see this in the example below. But if it's only defined on one side of an endpoint of the interval, then we understand that continuous at the endpoint means continuous from the right or continuous from the left. So whatever, what would naturally make sense. And we'll see how that plays out in this example now. So use the definition of continuity and limit laws to show that the function f of x equals x times square root 9 minus x squared is continuous on the interval -3 to 3 inclusive. Right? So we're including the endpoints -3 and 3. So the order of this doesn't matter. I chose to start by showing that the function is one-sided continuous at its endpoints. And then down below, I showed that the function's continuous in the interval. You could do that in reverse order if you prefer. Neither one depends on each other. So first and foremost, when we do the endpoints, we just have to think about -3 and 3. And this interval is including -3 and 3 with those square brackets. So then we want to consider whether or not the function is truly continuous at those endpoints. And the way to do that, well, I do it here for the endpoint x equals -3. And what we find is that, well, we just need to take the limit as x approaches -3 from the right. Remember, that's the leftmost point of our interval. So we've got to approach it from the right and just make sure that the limit of the function as we approach -3 from the right is equal to the function evaluated at -3. So when I evaluate this one-sided limit, I need to remember to use limit laws, right? So I have a product. So I'll take the limit of the product is equal to the product of the limits. I've split the limit over the product and applied it to each product term. The next thing I would do is I need to pass this limit inside the square root, right? So I'll do that. So here's where that happens. And I'm taking the limit now of 9 minus x squared. Then all I have to remember is that 9 minus x squared is a polynomial. We have a theorem that the limit of a polynomial is equal to the polynomial evaluated at that limit value, -3. This limit just became -3 because same rule, or the identity function rule also. So the limit as x approaches -3 of x is just -3. Just plug it in. Really, all of this looks like it's just a bunch of plugging things in, but I'm being very careful to evaluate my limits as I should, and this is why this turns out as it does. So I just plug in 3 to this one, or -3 to this one, because again, the limit law says you can do that for polynomials. So 9 minus -3 squared is +9. So 9 minus 9 is 0. So I have -3 times the square root of 0, which is 0. So I get a limit of 0 as x approaches -3 from the right. Now what happens for f of -3? F of -3, this is where I just plug it in. I get a -3 times the square root of 9 minus -3 squared. -3 squared is +9. 9 minus 9 is 0. Square root of 0 is 0. -3 times 0 is 0. So I left out some details, but very similar to what happened above. So the right-hand limit as x approaches -3 is equal to f of -3, and this is the statement I've written right here. And that indicates that f is right continuous at x equals -3. Now doing the same thing all for x equals +3 and approaching +3 from the left will show that f is left-hand continuous or left continuous at x equals 3. So then we'll have both of our endpoints done. That follows exactly as we've done it above, and I encourage the student or the viewer to do that on their own. Now, to show that the function is continuous on the interval from -3 to 3, these are all the values between -3 and 3. We need to choose a stand-in value, some representative of all the numbers, of any number actually, between -3 and 3. So a is a number that has the property of being between -3 and 3. So we've let a be an element of -3 to 3. In other words, we've let a be a member of the numbers in this interval. Other ways, just a few ways of saying that. Okay, so this means that f of a, if we evaluate f of a is definitely in the domain of f, right? That's where f is defined, right? These are values for which it's defined. We could check that. 9 minus a squared is going to be greater than or equal to 0 for any values that are between -3 and 3. But anyway, it evaluates to this. That's as far as we can take it. No simplifications necessary. F of a is just a times square root of 9 minus a squared. Now, is that equal to the limit of this function as x approaches a? Well, we need to take that one. The limit as x approaches a of f of x is this, right? F of x is x times root 9 minus x squared. And we just use our limit laws. We split the product as the product of the limits. And I've moved my limit inside the radical already. It's one of our other limit laws. So here we are at this. And I realize at each of these points, I can evaluate limit as x approaches a of 9 minus x squared, because 9 minus x squared is polynomial, so I can just plug a in for x. Similarly, for this one, I can evaluate at x because that's polynomial, so I can plug in a for x. When I do that, I have a times root 9 minus a squared. And what turns out to be the case is that the limit as x approaches a of f of x is equal to f of a. Those two things match. This is true for all a values between -3 and 3. So I can then conclude that f is continuous on the interval -3 to 3. And with that, and that's the open interval, with that and with the endpoints that we've shown, we can say that f is continuous on the closed interval -3 to 3 all the way through, because it's continuous at each endpoint. That's left and right continuous at each one respectively, and it's continuous for every number in between, so the function is continuous on the closed interval. Now, this example might have lost you. We had an abstract value of a here, then we made some arguments about how this thing's continuous for these values of a. That's okay that maybe you didn't follow along with this. Maybe the more instructive or the more useful thing for now is to know how to do the left-hand limits and compare that to the values, since those are explicit values of the variable x instead of being some arbitrary number a in -3 to 3. This is essentially this is a proof of this function f of x being continuous on this interval. And as students in Calc 1, we don't really need to be able to write many proofs. So hopefully this is just informative, but just a good demonstration of how, we prove things in mathematics, at least in a very specific situation like this. It's a good exercise for that, but again, note that you won't really have to prove many things in the course. We will have a couple times where we have to use theorems to show something, which is essentially proving too, but it'll usually be somewhat formulaic. All right, so let's move on to something maybe more tangible. We've got some very nice theorems regarding continuity of functions, and these really all follow from the limit laws of limits of functions. So if we have two functions, f and g, and they're continuous at a number a, at some value a, and then we have some constant c, and so some other real number, then the following functions are also continuous at a. So if we add two continuous functions together, the result is a continuous function. Subtracting two continuous functions gives us a continuous function. Multiplying a continuous function f by some constant c still gives us a continuous function. So on for products, and so on for quotients of functions. Remember, for quotients, you just have to be careful that g of a is not 0. Okay, so long as our denominator is not 0, our quotient of functions is also continuous if the two functions are continuous. And this set of results here is what finally brings us to the ability to conclude, and this was hinted at in the beginning of the video, any polynomial is continuous everywhere. So in other words, it's continuous on all real numbers, or the interval -infinity to +infinity. And then very similarly, any rational function is continuous wherever it is defined. So in other words, on all of its domain. And there we have it. So polynomials are continuous for all real numbers. Rational functions are continuous on their domain. So it's exactly what we would expect and what we would hope. And this has a lot to do with why we were able to just, when we took limits of polynomials or rational functions, why we could just plug those numbers in and get the values out. Because remember, what we were doing back then is the same thing that continuity tells us. The function f, if it's a polynomial, or if it's continuous at a, satisfies this property. We can just plug a into it. So when we recognize f as being a polynomial, we could just skip all the limit work and just say, well, it's just f of a, right? It's just the number, just plug it into the function. And that was true for rational functions so long as a was in the domain of that function. So there's a nice connection back to section 1.3. So let's do an example with this. Find the limit as x approaches 2 of 2x squared minus x minus 1 over x squared minus 1. Again, we have a rational function. They're getting a bit more complicated than our initial examples, but this is a polynomial divided by a polynomial. So this is a rational function. So the function's continuous on all of its domain. We just need to figure out what its domain is, so that way we'll know whether or not we can use the rule of just plugging in x equals 2. Well, they also ask us to determine where this function is continuous. This is the second part of this. So first thing to do is to find the domain of this function, right? We need to figure out where the function's defined and where it's not. So this thing is telling us the answer, this statement I have here, -infinity to -1, and then it looks like we've punched out a hole at -1, and similarly we've punched out a hole at +1. So the function's defined for all real numbers except for -1 and +1. Well, how did we do that? Just remember back to college algebra. You might have looked at the denominator, g of x, which is x squared minus 1, and you found the roots of this polynomial. So in other words, where is this thing equal to 0? You might set it equal to 0, and then you'd see that x squared is equal to +1 when you add 1 to both sides. And then you take the square root of both sides, you get plus or minus the square root of 1, which is plus or minus 1. Well, plus or minus 1 is exactly this value and this value that we've removed from the real numbers in order to express the domain of G. So there we have it. Those are the numbers that we can't plug into G. Those are where it is not defined. And those are places where it will be discontinuous, right? This function is discontinuous at +1 and -1 because it's not defined there, right? Those numbers aren't in its domain. So it's continuous everywhere else because it's a rational function, right? We've already seen this. It's continued everywhere it's defined. It's continuous on its domain. So that brings us to actually finding the limit of the function. Now that we know that we're approaching 2 and that 2 is in the domain of this rational function and the function itself is continuous at that point, well, then it's very easy to evaluate the limit because we can just use the substitution rule. We can just plug in 2 everywhere there's an x. And that's what that looks like to the right here. And once we get done simplifying all the arithmetic involved there, we have 8 minus 3 over 3 is 5 over 3, and that's our limit. All right, so our limit as well as the function value there, because we're able to use that nice rule that the function's continuous. You can evaluate its limit as the value of the function. There we go. And the function, as I said before, is continuous on this interval. So all values except for -1 and 1 on the number line. Okay, so generalizing or opening up our sets of functions that are continuous, we see the following, right? The more functions that we know are continuous, the easier it will be to take limits of these functions. So it turns out that the following types of functions are continuous at every number in their domains. And these are polynomials and rational functions, which is something we've already seen and are already convinced of. Root functions, so remember something like, the square root of x plus 7, that's a root function. That thing is continuous on all of its domain. Trigonometric functions, sine of x, cosine of x, tangent of x, they're all continuous on their domain. And that's all we get in the list so far. So that's nice. So we're kind of building up. We've added two sets of functions, root functions and trigonometric. So determine the intervals of continuity for each of the given functions. Well, cosine of x. Cosine of x is continuous on all real numbers, continuous for any real number, because cosine of x is defined for any real number. Remember that its graph is this sort of non-ending wave function, looks something like this. Any x value you can name is allowed to be plugged into that function, and we'll get a return y value between -1 and 1. Since it's defined for all real numbers, and above they tell us trigonometric functions are continuous on their domains, then we know automatically that cosine of x is continuous on all real numbers. So a root function, root x minus 1. It has domain +1 to infinity. We found that by setting x minus 1 greater than or equal to 0, and then solving for x, and we found that that's x is greater than or equal to 1. The interval where x is greater than or equal to 1 is 1 to infinity, including 1. So we know that here's the domain of this root function, and from the theorem above, we know that this function is continuous on all of these numbers at 1 to infinity. So I guess the one thing to check is this. If we approach 1 from the right-hand side, well, is the function going to be continuous here, right? And it looks like maybe there's an error in the notes I have here. So let's actually check this out. Approaching 1 from the left-hand side doesn't exist, so this thing doesn't have a limit as x approaches 1, doesn't have a two-sided limit because its left-hand limit doesn't exist. Well, that's reasonable, but the problem is we're talking about 1 to infinity. We're really only going to ever approach from the right-hand side. So to finish these are not wrong. This is all accurate information here. But to finish this analysis truly, I would check this real quick. The limit as x approaches 1 from the right of root x minus 1. This one does exist, right? We're plugging in values that are greater than 1. We're going to get 1.1 minus 1. We're going to have numbers that are slightly positive under the square root. That's well defined. So this actually approaches 0. We can do the square root of the limit of x minus 1 as x approaches 1 from the right. And we'll see that this is 0. And moreover, f of 1 is root 1 minus 1, which is a square root of 0, which is 0. The right-hand limit matches the function value at 1. So it turns out that this is actually wrong. This should be inclusive. The function's right continuous at 1. So it's continuous on this interval with a closed bracket at 1. It's continuous at 1 from the right, and it's continuous at all real numbers to the right of that. So that's a good correction to make in the notes there. So the tangent of x, right? Most of us probably thought for trig functions that tangent of x has vertical asymptotes, so it's going to have trouble with its continuity, right? However, as long as, remember, vertical asymptotes are points of the domain of, or points that are not in the domain of tangent. A vertical asymptote is an x value that is not in the domain of the function, and since we throw those out, then a tangent is continuous everywhere else. So between its vertical asymptotes, we have continuous curves for tangent's graph. You remember that. So where is tangent of x not continuous, right? So tangent of x is continuous for all x values which are not odd integer multiples of pi over 2. In other words, what we're trying to figure out is, what we're trying to point out are the values where cosine of x is equal to 0. So angles that we plug into cosine of x that make cosine of x 0 are angles like pi over 2, 3 pi over 2, 5 pi over 2, negative pi over 2, negative 3 pi over 2, and so on. And the way we wrote that back in trigonometry was to write 2k plus 1 times pi over 2. So, and k is any integer. So remember, this is a little formula that just picks up all the odd numbers we could possibly come up with, right? So when k is 1, then 2k plus 1 times pi over 2 comes out to, it's a 3 in parentheses, so it's 3 pi over 2. That's one of the angles I named, right? When k is 0, 2 times 0 plus 1 pi over 2 is 1 times pi over 2, so the output is pi. That's another one of the angles I named. When k is negative 1, I'll let you do the work here, but you get negative pi over 2. Right, so all of these odd integer multiples of pi over 2 come out of this formula. So this is a nice, concise way or mathematical way of listing all the numbers at which tangent of x is not continuous because it has a vertical asymptote there. So its limit doesn't exist at those points. Okay, lastly, we look at the floor function of x, or the greatest integer function of x. So this is continuous for all non-integer real numbers. Okay, so in other words, as long as we're not talking about 2 or negative 5 or any integer, then this function's continuous, right? Because remember, at each integer we saw in its graph, it jumps up to the next integer. So when we're moving from values that are 1 point something up to 2, by the time we get to 2 and exactly at 2, the function jumps up to 2 in its y value. So it's not continuous at integers, but it's continuous everywhere else. Okay, not lastly, but we're getting there. We have two more theorems here. If f is continuous at b, and the limit as x approaches a of g of x is equal to b, so this is a composition of functions result. And we can say that the limit as x approaches a of f of g of x is equal to f of b. So what that means is this. If f is continuous at g's output value, then we can evaluate the limit of f of g of x as simply plugging in b for f. So maybe a nicer way to say it is this, in other words phrased down here. The limit of the composition of two functions is equal to f of the limit of the inner function. And that's provided f is continuous at this b value that g approaches. Okay, that looks really complicated as a theorem. It's a little messy. It's hard to read, obviously. But we'll see it down below, and it'll be helpful for us to determine continuity of functions just by looking at them as compositions of continuous functions. And we'll see that in just a moment. And that's exactly what this theorem is doing, more in better language. If g is continuous at a and f is continuous at g of a, then the composite function or the composite function f of g is continuous at a as well. Okay, so if we compose two continuous functions, then we get a continuous function. So determine the intervals of continuity for each of the given functions. So we'll get to work on this. Cosine of x cubed. So now we've taken the function x cubed and plugged it into cosine. The outer function f is cosine. We're taking the cosine of something on the outside, right? So that's f. We know that cosine of x is continuous for all real numbers. Okay, that's what this means, on the set of real numbers. G of x is the inner function. The inner function in this case is x cubed. X cubed is a polynomial. We know it's continuous on the set of all real numbers. So f of g, which is cosine of x cubed, as we've written down below here, right, once we compose those two things, is continuous on the set of real numbers. So when we compose these two things, we get a continuous function. And notice there were no domain restrictions, so this is just true in general. Okay, so we might have to be more careful. In the next case, we'll see how we need to be so. So f of x over g of x. So this is more maybe a quotient problem than anything. And remember, we've got a theorem for that, right? back here, we can deal with quotients of continuous functions. In this case, we don't have a rational function, right? Because the bottom function is not a polynomial. So anyway, the domain, so the numerator function f of x is x to the fourth. Okay, so x to the fourth is a polynomial. The domain of f is all reals. F is continuous on the set of all real numbers. Okay, so is maybe not a good word. F is polynomial. And so let me say that. I'd rather say this one for sure. F is a polynomial. Okay. So we know it's continuous on all real numbers. Now, g, on the other hand, is a root function, and root functions are continuous on their domains. The domain of this root function is positive 1 to infinity, including positive 1, right? So g is continuous on, let me switch this. I don't like that I made that mistake in some past situation, but it includes 1. We've already showed that for this function. That's just a typo right there. So it's continuous from 1 to infinity. And now what we would be tempted to do is not be so careful and say, okay, the domain of f over g is 1 to infinity, exclusive of 1. And we want this to be the case. We need to exclude 1, not because of this, which includes 1, but because g is in the denominator, in other words, down here, and we can't allow g of x to be equal to 0. G of x is 0 when x is 1, so we have to exclude 1 from the domain of our new function f over g. But since f and g are continuous on their domains, and anywhere that g is not 0, we know that from 1 to infinity, which is the domain of this ratio of functions, we know that f over g is continuous from 1 to infinity. So we restrict the domain for our, in the set of numbers where the function is continuous, by whatever the domain of each function is, right? The first one didn't have any restrictions because it was polynomial. F was polynomial. G has a restriction because it's a root function, but even further, when we put them together as a ratio, we had to eliminate anywhere g was 0. So that's why we quit including 1. And then what we know is that f and g are continuous on their domains, so their ratio is continuous as well everywhere where that ratio of functions is defined. That's from 1 exclusively to infinity. Okay, we're almost there. Our last example involves our last result of the section, and this is the intermediate value theorem. So we suppose that f is continuous on the closed interval a to b, and we'll let n, capital N, be any number between f of a and f of b, where f of a is not equal to f of b. Then there exists a number c in the interval a to b such that f of c is equal to n. Okay, so that is really complicated sounding. I'm sure I'll spend more time in any live meetings talking more about this, but just to give you a quick idea, a quick picture of it, it looks like the following. We have an a and we have a b, and f of a is not equal to b. So in other words, the function has some variation possibly. So there's f of b up here. Here's f of a down there. And n is a number that's between f of a and f of b, the y values. So n would be right between these two values, maybe somewhere in here. What this tells us is that exactly what you would expect. If the function f is continuous, y equals f of x, if this is a continuous function, and n is a number between f of a here and f of b, as we've graphed it, then there must be a value c such that f of c is equal to n. In other words, we can find an x value that'll land us on n. What it's saying is that the curve has to pass through the value n, right? We have to have an x value that the curve passes through here. Okay, so this is really useful if we're looking to prove that a function has a root, right? It might not find the root for us, but it'll tell us what interval the root is in. So let's see that. So this is one of those rare cases where students will have to do some kind of a proof. This doesn't happen often, but this will be one of those types of problems. So this example says, prove that the polynomial x to the fifth minus 3x plus 9 has at least one root. Okay, so here we are with our polynomial, f of x. And for this function to have a root, well, it means that this is equal to 0. Okay, that's what we're looking for. So our strategy will be this: to prove that this thing has an x value that makes it equal to 0, rather than trying to solve it and factor it and do all these types of things that we know from algebra, we don't have to find the root. We just have to prove that a root exists. So what we need to do to show that this function has an x value that makes it 0 is we need to find a number that makes our function positive, and then we need to find a number that makes our function negative, because if we know that our function is positive somewhere, and then it's negative somewhere else, and it's continuous, which this is continuous because it's a polynomial, well, then we know that it must have an x value that sends it to 0, because its graph has to pass through the x-axis at some point. And that's the strategy. The book does an example like this as well, maybe a couple. And so all we're really looking for is to satisfy the conditions of this theorem, so that way we can come up with the conclusion. So this is how it works. Really, I'm just going to guess and check numbers. I'm going to guess numbers I really like. I might try f of 0. If I put in f of 0, I get positive 9. In this case, I did f of 1. Well, 1 to the fifth minus 3 times 1 plus 9. When I tally all that up, I get 7, which is greater than 0. So now I know my continuous function has a y value that's positive. Now I want to show that my continuous function f has a y value that's negative. And I might have to guess a few times. I might have tried -1. I might try -10, right? But it looks like -2 works out. -2 to the fifth minus 3 times -2 plus 9. Well, -2 to the fifth is -32 plus 6, and then plus 9. And when I add all this up, I get -17. The number doesn't matter as much as the fact that it's less than 0. So now I have an x value for my function that makes it positive, and an x value for my function that makes it negative. So somewhere between -2 and 1, there's a value c, an x value that I could plug in, right? Because f is continuous on this interval, because it's a polynomial. There exists a c between -2 and 1, such that f of c is equal to 0. In other words, the function has at least one root. There is this c. It's implied by the intermediate value theorem. So here I've formulated my argument. F is continuous on this interval, and it's negative for the left endpoint. It's positive for the right endpoint. So inside this interval must be a point where the function comes out to 0, and that's that value c. Again, note that the theorem does not tell us what c is. It just guarantees that such a c exists, and we know that it's in this interval somewhere. We could then use that to approximate the value c, but the theorem doesn't tell us how to do that. We'll need other methods later on to come up with that. So one last example that I won't finish, but at least leave here as a hint, or as an exercise with some hints, is to prove that the equation x equals cosine x has at least one positive solution. So at least one solution x from in the interval 0 to infinity. So if I look at this equation, x equals cosine x, I need to convert it into something that I can apply the intermediate value theorem to. So I need to turn it into a function equal to 0. So I subtract cosine x from both sides, and now I'm looking at this function, saying, okay, does the function x minus cosine x have a root, right? Is there an x value that makes this function 0? So your strategy is to do this, and I'll let the reader or viewer complete this on their own. We need a number a in 0 to infinity. So we need some positive number a, and we're going to guess and check. You're going to have to guess and check to find this. It's so that when you plug a in, the result is less than 0. If you can find another number b in this interval that makes this result greater than 0 when you plug it in, then you've got both a negative output of the function and a positive output. Between a and b, or b and a, will be a value c that makes this function x minus cosine x 0. That'll be c minus cosine c is equal to 0. So c equals cosine c, and you'll have proven that this equation has at least one positive solution. So you're looking for a that does this and b that does that, and then c will be in between those two numbers. So what I would recommend for guesses or guess and checks in this situation, maybe you look at a graph for some help, but think of things like x equals 0 or pi over 2, all of our special angles, pi over 4, things like that. If one of those is negative when you plug it in and another one is positive, then your c value is going to be between those two, and you'll be able to conclude that such a 0 exists by the intermediate value theorem. So that's it for section 1.5. That's a lot of material. It's going to take a lot of practice. These are the only proof-based questions that you'd have to be able to do for tests or things like that. The rest is a lot of nice calculation that we can do thanks to continuity.